Assalamualaikum and hi students. So this is a lecture video for BEKG 2443 Engineering Mathematics 2 for chapter 2 multiple integrals. We continue with the next 3 LOs that we need to cover. Okay, so to evaluate double integrals in polar coordinates, to apply double integrals to find the area, and a bit introduction to triple integrals. Subtopic 2.4 double integrals in polar forms. As mentioned as theorem 2.3, Fubini's theorem for R region in polar rectangles, if a function of R theta is continuous and bounded by R theta equal to limit of R, we have A to B, and alpha, for theta we have alpha to beta, then we have this region. Our limit is from A to B and theta limit is alpha to beta. So this is the region. And to solve for this region, we have double integral alpha to beta for theta limit and A to B for R limit. And then we have F R theta, the function, and then we have extra R here. Our dx dy now is r dr d theta, or you can write as r d theta dr. For definition 2.3, type 1 region, we have region that is bounded by the rays theta equal to alpha to theta equal to beta, alpha and beta, and by continuous polar curve r, the lower limit for r is g1 theta and r equal to g2 theta for the upper limit, lower limit and upper limit. And this is the region for type 1. For type 2 region that is bounded by r equal to A and r equal to B, and two continuous polar curve theta equal to h1r and theta equal to h2r. Okay, so this is lower limit for r and this is upper limit for r. And then it bounded by the curve of theta. Okay, theta, lower limit theta and upper limit theta. But normally we will solve for the type 1 region. We rarely find this type 2 region in this subject. As for the example, we have to find double integral for fr theta dA, given that fr theta equal to r cos theta and the region is bounded by this r and theta. So if we sketch the region, okay, we have theta. Theta is equal to, theta is from pi over 6 and pi over 2. It's between pi over 6 and pi over 2. So this is our pi over 2 and this is our pi over 6, the theta. This is theta equal to pi over 2 and this second theta is pi over 6. This whole is pi over 2. Okay, and then r is from 1 and 3, between 1 and 3. So this is 1, this is 3. This is our region R. Then for double integrals in polar coordinates, we have double integral, substitute our f r theta, so we have r cos theta, and do not forget that dA is equal to r dr d theta. Then substitute the limit for theta, we have our limit is equal to pi over 6 and upper limit is equal to pi over 2, and our limit is from 1 to 3. Okay, so this is equal to pi over 6 until pi over 2, 1 to 3. And then you have r here and r here. Do not forget this r. So you have r square cos theta dr d theta, and this is equal to pi over 6 pi over 2. We have 1 over 3 r cubed for limit 1 to 3 and cos theta d theta. Okay, and so for this one, we have equal to pi over 2 pi over 6 3 cube is equal to 27 divided by 3. We have 27 over 3. We have 9 minus 1 over 3 cos theta d theta. 9 minus 1 over 3 is equal to 26 over 3, and then need to do the integration for cos theta d theta. Cos theta, integrate cos theta, we have positive sine theta. So sine theta from pi over 6 to pi over 2. Substitute the value for theta. We have sine pi over 2 minus sine pi over 6. Okay. And this is equal to 26 over 3 sine pi over 2 is equal to 1, and sine pi over 6 is equal to 1 over 2. So 26 over 3 multiplied by half is equal to 13 over 3. Next, to change the Cartesian integrals into polar integrals, we have 4 steps. Okay, the first step is to sketch the region. So always start with sketching the region and label the bounding curve. Second step, instead of finding x and y limit, we find r limits and theta limits for the integration. Okay, and the third step is to substitute x equal to r cos theta and y equal to r sin theta. Okay, and the last step is to replace dx dy to r dr d theta. So the Cartesian integrals then become, okay, so from fxy dx dy we have f r cos theta r sin theta. So this is x and y. R dr d theta is dx dy, where g is the region of integration in polar coordinates. And then we need to solve the integration. Okay, in second steps of changing the Cartesian coordinates into polar coordinates, we have to find the r limit and theta limits. Okay, how to find the limits for r and theta? So there is 4 steps. Sketch the region. Okay, this is redundant in the with the first steps of changing the Cartesian to polar. Okay, so we can just use the same steps. The second step is to find the r limit of the integration. Use a ray L from the origin cutting through r. Okay, then mark the r values where L enters and leave r. Okay, so this is for radian, limit for radian. And then the third step is to find the theta limits. Okay, theta limits, the smallest and largest theta values. And the last step is to write the double integral and solve it. And this is the same steps as I mentioned in changing the Cartesian to polar steps. Okay, let's see few examples here to change Cartesian form to polar form. Okay, for the first example, by changing the integrand from Cartesian to polar coordinates, evaluate 0, 1, 0, square root 1 minus x square for x square plus y square, square root of it, dy dx. Okay, you need to change this Cartesian to polar. For the first steps, always sketch the region. For this one, from here, you know that the y limit is from 0 to square root 1 minus x square. And the x limit is from 0 to 1. Okay, to sketch it, x and y. So this is your y, this is your x. Y from 0, and then y, you have y equal to square root 1 minus x square. So again, this is y square plus x square equal to 1, which is a circle with radius 1. So you have a circle with radius 1. Okay, and then the y limit is from 0 to y equal to 1 minus x square. Then for x limit, you have limit from 0 to 1. So our region is here. Okay, quarter of your circle. And then for the second steps, find the R limit and theta limit. For R limit, R is radius. So the radius here is 0 to 1. Radius is from 0 to 1. And the theta limit, okay, so theta from here you have 0. Theta here is 0. Theta here is pi. The full circle is 2 pi. And the quarter circle is pi over 2. So the theta limit is from 0 to pi over 2. And then for the third steps is to substitute dx dy. Substitute x equal to r cos theta, y equal to r sin theta, and dx dy equal to r dr d theta. So you have double integral 0 to 1, 0 square root 1 minus x square, cube square root of x square plus y square dy dx. Okay, so for this one, you have double integral, substitute x square plus y square. X square plus y square, for this one, x square plus y square is equal to r square cos square theta plus r square sin square theta. And then r square cos square theta plus sin square theta. From trigonal identity, this cos square theta plus sin square theta is equal to 1. So x square plus r square is equal to r square. Remember this. Always remember that x square plus y square, when you change from Cartesian to polar, is equal to r square. So from here, substitute this x square plus y square square root. So you have square root of r square. And then dy dx is equal to r dr d theta. Then from here you have double integral r, this is r square, square root of r square is equal to r, multiplied by r, you have r square, dr d theta. Okay, then for last steps is to substitute your r and theta limit. Okay, for r limit is from 0 to 1. And then you have theta is from 0 to pi over 2. Okay, and then solve for this one. We have 0 to pi over 2. Integrate r square, we have r cube over 3 from 0 to 1 d theta. And then continue this, you have 0 to pi over 2. Substitute 1, you have 1 over 3 minus 0 d theta. Then from here, you have 1 over 3 theta from 0 to pi over 2. So 1 over 3 multiplied by pi over 2 minus 0 is equal to pi over 6. Let's see the second example. Evaluate double integral exponent x square plus y square dy dx, where R is the semicircular region bounded by the x-axis and curve y equal to square root 1 minus x square. So first, sketch the graph. Sketch for the region. We have y and x. Okay. And then you have y equal to square root 1 minus x square. And you know this is a circle with radius 1. So this is 1 minus 1, 1 minus 1. And then it states here that R is the semicircular region, meaning that you have semicircular region bounded by x-axis. This is your x-axis. And this is your the curve where y equal to positive 1 minus x square. If it says semicircular region, but this is y equal to minus, if you have minus here, so meaning that this is the region you consider, because this bottom part is equal to y equal to negative square root 1 minus x square. Okay, lower semicircular. Okay, and then you have double integral exponent x square plus y square dA is equal to, in polar form, we have double integrals, and then we have exponent, again x square plus y square. As I showed before, it is equal to r square. dA now is r dr d theta. Okay, and then what is our r limit? Our r limit is, okay, remember that r is radian, not diameter. So r is not from negative 1 to 1. It is from 0 to 1 instead. Radius is from 0 to 1. And then for theta, quarter is pi over 2. And then if you have semicircular, this is pi. The whole circle is equal to 2 pi. So for here you have 0 to pi. Integrate exponent r square r dr d theta. Use substitution, integration by substitution. Okay, so let u equal to r square. So du is equal to 2r dr. Okay, so r dr here substitute with du. So r dr is equal to, for r dr we have du over 2. So you have exponent r square now is u. So exponent u, r dr is equal to 1 over 2 du d theta. Okay, and then the limit, this is limit for r. Now what is limit for u? Substitute r into u. So 0 r square, so u is 0. R square 1, so u is equal to 1. So I have 1 over 2 here, and then 0 to 1, integrate, pi to 0 to pi, integrate exponent u is exponent u from 0 to 1 d theta. So I have 1 over 2, 0 to pi, exponent u is exponent 1 minus exponent 0 d theta. Exponent 1 minus exponent 0 is constant. Okay, so we can write it outside. So this is exponent 1 minus exponent 0 is equal to 1. So you have 0 to pi for d theta, 1 d theta. So 1 over 2 exponent 1 minus 1 theta, integral 1 respect to theta is theta. So for this one, I have half exponent 1 minus 1, substitute pi minus 0, I have pi. So this is the last answer. And the third example I have here is to evaluate double integral 3x plus 4y square dA, where R is the region in the upper half plane bounded by the circles. Okay, you have two circles here. Okay, one is x square plus y square equal to 1, and another one you have x square plus y square equal to 4. So you have two circles. The first one is a circle with radius 1. And the second one, you have a circle with radius 2. So basically, this is the region. So bounded by this. So you have this. Okay, so this is the region. Closed region. Okay, and then it mentioned here, R is the region in the upper half plane. So upper half plane means you need to consider just this region, not the whole plane. Okay, so for this one, if you write the double integral, okay, so 3x, substitute x with r cos theta. X is equal to r cos theta. plus 4y. Y is r sine theta square. And dA is equal to r dr d theta. Okay. So for this one, r limit is from 1 to 2. So 1 to 2. And your theta limit is from 0 to pi. So this is 0 to pi. Then for this one, simplify this. You have 1, 2, 3r square. Do not forget this r. Okay, so 3r square cos theta plus 4r square multiplied by r. Here we have 4r cube sine square theta dr d theta. Okay, integrate r first. You have 3r square. You have 3r cube over 3 cos theta plus 4r to the power of 4 divided by 4 sine square theta. R from 1 to 2 d theta. From here, substitute the value for 2 and 1. You have 8 cos theta plus 2 to the power of 4 is 16. 16 sine square theta minus with cos theta, substitute 1, minus with sine square theta d theta. Then again simplify. You have 0 to pi. 8 cos theta minus cos theta. We have 7 cos theta plus 16 minus 1. 15 sine square theta d theta. Okay, do the integration. Okay, you can use the property. So you have 0 to pi 7 cos theta d theta plus 15 0 to pi sine square theta d theta. Okay, so you can directly solve for this first integration. So 7 cos theta is equal to 7 sine theta. Substitute 0 to pi. Okay, but for this part, you need to substitute. Okay, sine square theta using the trigonometric identity. So using trigonometric identity, you know that the sine is 1. Okay, so constant, so I put it outside 15. Sine square theta is equal to half. Okay, half 1 minus cos 2 theta d theta. Please refer to the attachment appendix. Okay, so this sine square is equal to half 1 minus cos 2 theta. So for this one, you have 7 sine pi minus 7 sine 0 plus, for this one, you have 15 over 2, and then integrate 1 respect to theta. You have theta minus cos theta will be sine 2 theta divided by 2. Okay, and this is from 0 to pi. 7 sine pi, 7 sine 0 is equal to 0. This 2 is equal to 0. Okay, so plus with 15 over 2, substitute theta equal to pi minus sine 2 pi divided by 2 minus 0 plus sine 0 over 2. Again, sine 2 pi is equal to 0 and sine 0 is equal to 0. So the last answer is 15 over 2 multiplied by this pi. Okay, so 15/2 pi. Okay, so from here to here, you need to use trigono identity. Okay. Next is to find the area in polar coordinates. So the area of a closed and bounded region R in the polar coordinates plane is A equal to double integral R dr d theta, because our function fr theta is equal to 1. It's just the same concept as in Cartesian coordinates. Okay, we integrate 1. So for example, sketch the region bounded by R equal to 2 and R equal to 4. Theta 1 equal to pi/2 and theta 2 is equal to 2 pi/3. Find the area of the region bounded. Okay, so sketch the region. Okay, so theta is pi/2. Theta pi/2 is this one. This is theta equal to pi/2 and theta equal to 2 pi/3 is somewhere here. So this is theta equal to 2 pi/3. R equal to 2 and R equal to 4. So we have this R region. This region R. Okay. So for this one, to find the area, A is equal to double integral fr theta is equal to 1, and then we just have R dr d theta. The lower limit for R is equal to 2. The upper limit is 4. The lower limit for theta is equal to pi/2. Upper limit is 2 pi/3. So for the area, we can calculate for the area, we have pi/2, 2 pi/3, R, integral R, we have 1/2, R square, limit from 2 to 4, d theta. From here, substitute the value for R. Limit, I have 1/2, 4 square minus 2 square, d theta. And this is equal to 4 square is 16 minus 4, 8 divided by 12. So I have pi/2, 2 pi/3, 6 d theta. Okay, and last, integrate theta, we have theta. Integrate 1, we have theta. Pi/2, 2 pi/3. Last, I have 2 pi/3 minus pi/2 is equal to 1/6 pi. So the last answer is pi. The area for this region is equal to pi. Okay, moving to subtopic 2.5, triple integrals in Cartesian coordinates. Okay, definition 2.4 is about the triple integrals. So function, three variable function f, x, y, z defined on rectangular box. We define the triple integrals of f over g as this. Okay, so triple integral g f, x, y, z dv is equal to limit of f, x, y, z. Okay, provided the limit exists. The limit must exist and is the same for every choice of evaluation points xi, yi, zi. Okay, for I from 1 to n, when this happens, we say that f is integrable over g. And then we have theorem 2.4, the properties of triple integrals. So these properties are so much similar to the properties I explained in double integrals. So we have constant multiple, we have sum and difference, and domination additivity. Okay, it just instead of we use this double integral, we use triple integrals here, but the properties are just the same. In theorem 2.5, we have Fubini's theorem for triple integrals. Function f, x, y, z, three variable function is continuous on a box shaped region G of the form. Okay, so this is the limit x, y, and z. We have limits x a to b, c to d is for y, and z from k to l. Then this triple integral can be written as dx dy dz with appropriate limits of x, y, and z, and the order of integration in the iterated integral can be interchanged. The above iterated integral is one of the 6 possibilities. Okay, so here you have dx dy dz. You might have dy dx dz, or dz dx dy, or dz dy dx, and so on. Okay, but make sure to change the limit accordingly. Okay, if you have x here, and if you have dz dx dy, so make sure this is limit for z, this is limit for x, and this is limit for y. Example, evaluate the triple integral 12xy square z cube dv, where g is the rectangular box given by g, okay, limit x, limit y, and limit z. Okay, so for the triple integrals, see triple integrals for 12xy square z cube. Okay, let's say for dv, I want it to be dx, dy, and dz. So I must write x limit first inside -1 to 2. Continue with y limit 0 to 3, and the last one is for z limit 0 to 2. This is equal to 6, 4, 8. Okay, so you can try with dz dy dx. Okay, so the last answer should be the same, 6, 4, 8. Or you can try with triple integral 12xy square z cube dy dx dz. Okay, so this one 0 to -1 to 0, 3. The last answer is the same as well. Okay, any combination of dy dx dz, it will give the same answer. And for the last example in this video, we try to evaluate triple integrals for exponent z sin y dz dy dx. Okay, given the limit for dz dy dx 0 pi over 2 0 to 1 exponent z sin y dz dy dx. Okay, so this is equal to from 0 to 2, 0 to pi over 2. Integrate exponent z respect to z is equal to exponent z. So limit 0 to 1 dy dx. So this is 0 to 2, 0 to pi over 2 exponent z, substitute 1 minus exponent 0 dy dx. Okay, put it outside, exponent 1 minus 1. So I have 0 to 2, and then, oh, I missed the sign. Sin y dy. So this, I have sin y dy here. Okay, so integrate 0 to pi, and then integrate sin y respect to y. We have negative cos y from 0 to pi over 2 dx. So exponent 1 minus 1, 0 to 2, negative cos pi over 2 plus cos 0 dx. So this is equal to exponent 1 minus 1. Okay, substitute the value of negative cos pi over 2. Negative cos pi over 2 is equal to 0 plus cos 0 is equal to 1 dx. So exponent 1 minus 1, integrate 1 respect to x. I have x from 0 to 2. So here I have exponent 1 minus 1 multiplied by 2 minus 0. So my last answer is equal to 2 exponent 1 minus 1. Okay, for triple integral over rectangular region. Okay, that's all for today's lecture video. So for the next lecture video, I will continue with triple integrals over non-rectangular region. And subtopic, the next subtopic we have is triple integral in cylindrical region. Thank you.